pleased to introduce to you Dr. Ariel Cohen to deliver this series of lectures on convective outlook forecasting. Ariel and I began this collaboration in the summer of 2017 with a desire to develop a set of practical training resources aimed at helping forecasters to understand better the kinds of ingredients they need to be looking at when trying to diagnose potential for convective initiation, for convective mode and evolution, and certainly associated hazards. And it's really important for any forecaster, regardless, you certainly don't have to be a National Center SPC forecaster. It's important for every forecaster down to the local level to be thinking through these ingredients and these processes when deep moist convection is possible in your area. So for me, an important aspect of this was to find someone who can bridge theory and operations. And for my money, there are a few people in the National Weather Service better qualified to meet that demand than Ariel Cohen. I mean, from an operational perspective, he's served in multiple forecast offices. He's been at the National Hurricane Center, served for 7 years at SPC as convective mesoanalyst and outlook forecaster. And all the while working rotating shifts, completed his PhD at OU. So that gives you a feel for his dedication and his work ethic. And certainly one of the things that I appreciate most is that in addition to being extremely knowledgeable about meteorology in general and convection in particular, Ariel is passionate about teaching others. And he has a rare gift of being able to take complicated subject matter and break it down in a way that is understandable and easy to apply. And so with that as background, it's my privilege to introduce my respected colleague and good friend, Ariel Cohen.
Thank you very much, Kim. Well, one of the areas that I don't have a lot of experience in is baking. But I do know from my friends and family that there are certain ingredients that all have to come together at the same time and place in order to bake a cake, like flour and maybe milk and sugar and baking powder and maybe some other things as well. But you don't get a cake or a good cake without having all of these ingredients come together at the same time and place. And this is very analogous to the ingredients or necessary conditions that must all come together at the same time and place to support the development of organized severe thunderstorms. And that's what we're going to be talking about throughout these lectures, is the ingredients for organized severe thunderstorm development. That's what we're forecasting for. And as I indicated, that we have these necessary conditions: moisture, instability, lift, and vertical wind shear, that must all come together at the same time and place in order to foster the development of organized severe storms. Now, when we're talking about the vast expanse of points throughout the entire contiguous United States, over the course of 8 days over which we're issuing convective outlooks for, it's absolutely critically important that we understand the circumstances that come together to foster the mutual overlap of moisture, lift, instability, and vertical wind shear. And very importantly, the underlying physical principles that govern that mutual overlap of the ingredients. We don't want to be caught off guard by any of the more trickier, nuanced patterns that could support the overlap of these conditions. And it's going to be very important that we be able to really understand the details and some of the variations of the more commonly repeatable patterns so that we can maintain that situational awareness to be able to identify those details that support that overlap of those necessary conditions supporting organized severe storm development. And that's what we're going to be talking about throughout this presentation. Because remember, after all, it's those critical details that us as meteorologists can really hone in on to identify some potentially very sneaky severe weather episodes. And that's going to be very important in terms of messaging that information to protect life and property. We're going to be talking about the scientific foundation here throughout these lectures so that you can have the tools and resources to be able to perform that severe thunderstorm threat assessment from a very apparent scenario to a very, very subtle type scenario. So I'm going to pose a question. What purpose does organized severe convection play in this world? Is it just a happenstance, circumstantial response to the mutual overlap of those necessary conditions, moisture instability, lift, and vertical wind shear, or is there a bigger purpose as far as why organized severe convection evolves in the world overall as a physical entity? What it'll actually demonstrate is it's more than just a happenstance response to the mutual overlap. It's part of a bigger process, and we're going to talk about that right now. So let's get started with that. All right, let's take a look at the planet over here. We know that across the planet there are imbalances in solar heating between the equator and the poles. Specifically, toward the equator we have very hot, humid conditions compared to the polar regions. We'll just focus on the North Pole over here, where it's considerably cooler and drier. And so the imbalances in solar heating between the equator and poles effectively establish a meridional temperature gradient, which I'll just mark between here as this gradient and potential temperature, and equivalent potential temperature, as well between the equator and poles. This meridional temperature gradient is the impetus for baroclinic instability. That is the manifestation of available potential energy associated with the baroclinic instability related to the meridional gradient in potential temperature and temperature. And so this instability, this baroclinic instability, is going to be the direct result of the imbalances in solar heating across the planet. And we know that the atmosphere does not like instabilities. And so things are going to happen, which I'll talk about in just a moment, so that the atmosphere tries to relieve itself of the baroclinic instability by converting available potential energy to motion or kinetic energy. We'll talk about that in just a moment. So let's imagine we have some mid to high level circulation aloft, some cyclonic circulation aloft, come and interact with that antecedent baroclinic instability associated with a thermal gradient. The net result of that is going to be upward motion preceding that disturbance associated with differential cyclonic vorticity advection, which we'll talk about a little bit more shortly, that's going to support the development of a surface cyclone. And that surface cyclone, what it does, and I'm going to change colors over here. That surface cyclone comes along once our mid-level perturbation, our disturbance, cyclonic perturbation in the atmosphere comes along. And when we get our surface low form, it will have a tendency of transporting that hot, warm, humid air northward while pulling cooler, drier air towards the south. And in that process, that warm advective process in advance of the surface low, is going to have a tendency of resulting in mid-level height rises from the quasi-geostrophic chi equation. And the cold advection on the backside of the surface low, it will support the amplification of the cyclonic perturbation aloft as we get height falls occurring above the level of maximum cold advection, and then an amplification of the mid-level pattern that supports an increase in differential cyclonic vorticity advection. This very synergistic feedback gets going between the surface low and the mid-level wave that continues to support the constructive development of this deeper wave pattern. We continue to pull warm, humid air, higher theta E air to the north, where it was previously cooler and drier air to the south. And what happens? Well, we're taking the hot, humid air to the north, pulling the cooler and drier air to the south, and that mitigates that thermal gradient as the warm air is brought to the north, cool air brought to the south, and that meridional thermal gradient begins to diminish. In other words, by the process of the surface cyclone, it's acting as a remedy for the baroclinic instability that had initially developed because of the meridional thermal gradient. And so this cyclone, we can really think of the cyclone as an instigator to removing the baroclinic instability, a manifestation of the conversion of available potential energy to kinetic energy through the motions that are occurring through the synergistic feedback process between the surface cyclone and the mid-level wave to relieve the atmosphere of baroclinic instability. So great, surface cyclone comes along, we're reducing baroclinic instability, converting available potential energy over to wave-like motions, but in the process of bringing warm, humid air to the north beneath potentially relatively cooler conditions in the mid-levels of the atmosphere, we're generating a new type of instability called convective instability, and that's going to be associated with CAPE. And let me mark that over here. So by bringing the warm, humid air northward to relieve the atmosphere of baroclinic instability, we end up generating convective instability, and that is going to be associated with CAPE, analogous to baroclinic instability being associated with available potential energy. So we generate as this convectively unstable scenario by bringing the warm, humid air northward beneath relatively cooler air aloft at the same time, of course, with the intensification or amplification of mid-level height pattern that would also have a tendency of potentially strengthening mid-level flow, strengthening deep shear in the vicinity of this buildup of convective available potential energy. And so all of these processes are effectively supporting an overlap via the cyclone. The surface cyclone that's responding to a release of available potential energy is actually just organizing the favorable ingredients for organized severe convection. So we get this buildup of CAPE, of convective instability, as we transport the warm, humid air northward to relieve the baroclinic instability. So we've generated convective instability, we've generated CAPE, and the forcing for ascent accompanying the surface cyclone as intensified by the mid-level wave pattern and those characteristics therein would then support the development of convection, which are associated with vertical motions that support the release of convective instability via the conversion of convective available potential energy to convective overturning related vertical motions. And so it's really a two-step process by which the imbalances in solar heating drive an instability that support surface cyclone development that organizes, and I want to say really deeper cyclone development, that organizes favorably the ingredients fostering organized severe storm development that are then released finally by the convective overturning process. So really we could think of this cyclonic perturbation and its interaction with the mid-level perturbation as being a key remedy, that in addition to the convection, to the release of these instabilities that are all instigated initially by imbalances in solar heating between the equator and the polar regions. And so when we think about convective processes in this manner as being very much tied to more of a global circulation and global heat balances, we kind of see the purpose that convection plays in terms of the mitigation of instabilities. The atmosphere does not like instabilities. It doesn't like imbalances. It wants to get back to a balanced state. It wants to remove instabilities. And so this process of cyclone development and organizing favorable severe storm ingredients and then the release of those instabilities in those processes is absolutely critical towards considering bigger scale, larger scale processes favoring organized severe storm development. So again, we talk about these ingredients for organized severe storm development: moisture, instability, lift, and vertical wind shear. And when we talk about quantities like moisture, I don't want to say it's easy to measure those, but there's a lot of measurements and models that can help lead us to some idea, or at least ballpark, what types of or amounts of moisture are present in various layers of the atmosphere. We can use mixing ratios, specific humidity, dew points as gauges for the amount of moisture and its distribution within the vertical profile. Instability, and we're talking about lapse rates, and it's the combination of lapse rates and moisture that give us buoyancy, which can be integrated through the vertical profile to get that convective available potential energy. So these are things that are somewhat quantifiable and some processes that we can either calculate, or I should say variables or presenting processes that we can potentially calculate and even measure in some circumstances. So that's moisture, instability, vertical shear. We can consider vector wind differences to get bulk shear computations. We can take vertical integrals of streamwise vorticity to get storm multiplicity calculations. But one of the most challenging ingredients to be able to really gauge or quantify in particular is the lift. The lift is one of the most challenging ingredients that we can possibly gauge, forecast for, etc., because it's going to be very much related to divergence calculations, which is linked to mass conservation. The divergence in the atmosphere and the differential divergence go into supporting the vertical motion tendencies that potentially support or mitigate severe convection. And it's the lifting ingredient that has some of the most potential error accumulated, as divergence calculations are largely fraught with error in them, and when we vertically integrate them through the column, we just keep on accruing more and more error. That actual calculations of omega are highly sensitive to grid length. There's a lot of approximations and errors that make it very challenging to actually quantify vertical motion, particularly separating that between synoptic scale, mesoscale, and storm scale. And so we really are going to be seeking out as much guidance from quasi-geostrophic theory to really understand where the lifting ingredient plays a role in terms of influencing the development of organized severe convection. And so we're going to focus a lot on that, acknowledging the fact that moisture, instability, and shear certainly challenges in measuring those and forecasting those, although their quantification is a bit more straightforward than the lifting ingredient associated with organized severe storm development. So let's spend a lot of focus on that lift ingredient so that you get an idea about its role in supporting severe storm development. You can have a completely conditionally favorable severe storm environment with lots of instability, moisture, and vertical shear, but if there's absolutely no source of vertical motion or upward motion to support the development of storms, that environment stays nothing more than a conditionally favorable environment. All right, so let's talk about lift. When we talk about vertical motion, the lift ingredient for organized severe storm development, we're going to be appealing heavily to quasi-geostrophic theory. We can consider lift as being a response to imbalances in the atmosphere, and I'm going to talk about how the quasi-geostrophic omega equation is addressing those imbalances on the right-hand side, or the forcing terms, and how the vertical motion is a response to those imbalances to get the atmosphere back to that balanced state that it likes to be in. So let's go to the quasi-geostrophic omega equation, and we're going to talk a little bit about equations. We're not going to spend a lot of time on equations, but there's some very important ones because they describe conceptually and qualitatively as well what's going on in the atmosphere to foster the development of organized severe storm development. So let's think about this semi-qualitatively and quantitatively. Quasi-geostrophic omega equation says that del squared of omega, or the Laplacian of omega, which is going to be in pressure coordinates, is going to be related to the combination of differential vorticity advection and thermal advection. And so let's take a look at what del squared omega is. Well, if we think of the atmosphere as being largely sinusoidal wave patterns, take the first derivative of sine, we get cosine, then take the derivative of that, we get minus what we start out in the first place, sine. So that's just making the del squared, the Laplacian operator, act as a negative sign, negative omega. But negative of omega, that's just going to be in pressure coordinates. We can back out into height coordinates over here, such that this is really behaving as W. So W over here, that is the dz dt, vertical motion component of the motion in the vertical using height coordinates specifically. Let's then put that W in here on the left-hand side, and we can think about this as being a response term vertical motion response is the result of forcing from differential vorticity advection and thermal advection. But these are not just generic mathematical terms. There's a meaning behind each of these. Actually, differential vorticity advection, it's less challenging mathematically than you may think it is. When we think of differential vorticity advection, we're just talking about an imbalance, or specifically a deviation from geostrophic balance. That is, one where the Coriolis force and the pressure gradient force are in balance. We have deviations from that, like when we get divergent motion. Remember, divergent motion is inherently ageostrophic because the divergence of the geostrophic wind is 0. So when we have divergence in the atmosphere, that is very much linked to what this term is, and specifically differential divergence. Let's think of this conceptually. If I'm an air parcel and I'm in the base of a trough, and I'm traveling through the trough, because remember, the actual motion through the trough exceeds the actual phase velocity magnitude of the trough itself, then I'm going to have to lose spin when I depart the trough. Now, the only way I can lose spin is by laterally expanding and enhancing my divergence in the mid and high levels of the atmosphere so I can spin down as I depart the base of the trough, resulting in enhanced divergence aloft. Those conditions are muted as we get lower in the atmosphere, closer to the ground, where frictional effects play more of a role. And really, that differential divergence is going to support that upward motion so we can fill that evacuation of air at the top of the column, and we're maximizing the divergence so that we spin downstream of the trough. Well, what's downstream of the trough? That's where we have cyclonic vorticity advection that increases with height above ground, giving us differential cyclonic vorticity advection, also known as differential positive vorticity advection, DPVA. I'll use that interchangeably with DCVA. Well, that's just differential divergence, and that's embedded in this term representing a deviation from geostrophic balance. So the atmosphere is pulled away from geostrophic balance, this term activates, and then it's brought back into balance by supporting the vertical motion in order to assume that balanced state of geostrophic balance once again. On the other hand, for thermal advection, that represents, when it's non-zero, a deviation from hydrostatic balance, which is a balanced state in the atmosphere in the vertical between the upward directed pressure gradient force and downward directed gravitational force. And when the atmosphere is pulled away from hydrostatic balance, when we have thermal advection, the vertical motion response results in a tendency for the system to be brought back into that balanced state of both hydrostatic balance as well as geostrophic balance over here. And again, when you think about thermal advection occurring within a zone of ascent preceding some deeper cyclone, along with differential cyclonic vortice advection, these processes that are the forcing terms for vertical motion are inherently tied to that cyclonic perturbation. So that cyclonic perturbation, which is serving as a remedy for baroclinic instability mitigation and conversion of available potential energy, is also working to support the vertical motion fields as it is also yielding, and its progression yields these imbalances. And so really the cyclonic perturbation is so key to organizing severe storm ingredients, supporting the conversion of available potential energy to motion as we mitigate baroclinic instability, supporting the vertical motion, etc. It really does so many things. It does a wonder of things in order to really tie all of the concepts together in a unifying theme. So we're going to really look back at what the cyclonic perturbation is doing in terms of influencing these terms, because this W over here, we get the conceptual ideas I talked about over here, but this is going to be something, again, that's going to be hard to quantify. So we're really going to be appealing to even more of quasi-geostrophic theory to get some idea of what W is, which we'll do right now, since we have some conceptual understanding. So let's now go to the quasi-geostrophic chi equation, or the height tendency equation, which tells us that del squared chi is going to be related to vorticity advection, losing the differential part, and differential thermal advection. And let me put my del squared here. And so that's the Laplacian of chi. And again, talking about wave-like motion in the atmosphere. So del squared chi is really going to be behaving as minus chi. And so when we have, let's talk about a very specific case before we go much more into this. Let's say that we were to have a wave pattern in the atmosphere that's not amplifying. That is one that is a steady state wave pattern in the mid-levels of the atmosphere. So effectively, what that means is that this term, the differential thermal advection for a steady state, goes to 0 for steady state case. And what that really means is that when we have substantial amounts of thermal advection, driving differential thermal advection taking place, let's say a large amount of cold advection behind a surface cold front beneath the base of a mid-level trough, that cold advection, or above the level of maximum cold advection, is going to result in the column of air thinning, consistent with the hypsometric equation, and height falls in the mid-level, and an amplification of the mid-level wave pattern related to the thermal advection driving the differential thermal advection above the level of maximum cold advection. And as a result, when we remove the case of amplifying wave patterns and just focus on the steady state wave patterns, we can allow this term to go to 0 and focus on the relationship between vorticity advection and height changes. So ahead of a shortwave trough, for instance, where we have positive vorticity advection or cyclonic vorticity advection, this is going to be positive, and so chi will be negative to keep the left-hand side positive and consistent with the right-hand side. So where we have positive vorticity advection ahead of a shortwave trough, or cyclonic vorticity advection, we're going to see, and let's write this case out, for the case of cyclonic vorticity advection, that is going to correspond to chi being negative, or height falls. That's what that means, or height falls where we have positive vorticity advection or cyclonic vorticity advection ahead of shortwave troughs. So we have these height falls. Well, that's something we can measure. We can actually look at the change in the mid-level heights over 12-hour time periods, for instance, and then use that information to gauge cyclonic vorticity advection. But cyclonic vorticity advection, we know typically is going to be increasing in magnitude with the height above ground as we depart the friction stunted flow in the boundary layer, and then we get stronger cyclonic vorticity advection with height above ground, yielding differential cyclonic vorticity advection, which is going to be positive, therefore in the case of height falls, and results in positive W, or negative omega, or upward motion. So height falls are inherently linked to upward motion in the atmosphere via the simultaneous consideration of the quasi-geostrophic omega equation and the quasi-geostrophic chi equation. And so that's something we can directly measure. Our height changes, and they're going to be linked inherently right to vertical motion fields. Where we have height falls, something we can measure, we can diagnose the amount of vertical motion, at least in a semi-quantitative, qualitative pseudo manner. So we're able to really retrieve a lot of information by considering some of the atmospheric properties that we can measure, like height changes. Also, when we're looking at a surface chart, let's think of what's going on where we see a zone of warm advection, or positive thermal advection. That's going to result in this forcing term being positive, and so we're going to get a response such that W is also positive, which is going to associate with vertical motion. Well, we have warm advection occurring. That's going to be marked by a zone of decreasing density. As the column expands, the density is going to decrease, and the pressures are going to be falling at the surface under those conditions. And we can measure pressure tendencies, pressure changes. Look at a surface chart, and you can get 2 to 3 hour pressure changes. Where we see pressure falls, there's going to be at least some linkage to upward motion as we apply quasi-geostrophic theory. So all of these factors are going to be very important, particularly when we're talking about a more strongly forced wave scenario. So mid-level height pattern, we put a surface low over here within the region of DCEA. We'll be having upward motion, height falls ahead of that disturbance. Cold front, here's a warm front, warm advection near and north of the warm front boundary. And these are going to be very much factors that are, if you want to say, more self-evident, more in a strongly forced regime where we have some more apparent mid-level wave scenario. That's going to represent a large number of more organized severe storm environments in terms of the synoptic scale. But there are going to be many variations on that pattern, many nuances on that pattern, which you're going to see illustrated throughout these short video clips of me performing a convective outlook update on the day shift for a day 2 convective outlook, which you'll be seeing shortly. In fact, you're going to be seeing in this first video clip a focus on where these ingredients are for an upcoming outlook, where the sources of these ingredients are, their magnitudes, their locations, what we're talking about here, and a particular focus on the eventual landfall and associated tornado threat of Hurricane Harvey going back over a year ago. You can think of this hurricane as also being one of these circulations that's serving as a remedy for instability releases, various forms of atmospheric instability releases. And you'll see how a lot of these different patterns and big-scale unifying theories are actually acting at a smaller scale relative to that landfalling hurricane to support the enhanced or heightened tornado risk in the vicinity of the Texas coast. And so really the focus on the details within these patterns and having that underlying physical understanding will be key to being able to identify the severe thunderstorm potential and perform an accurate severe thunderstorm threat assessment.